we've seen that if you just have a given function like this blue line, and you want its antiderivative, that's going to be the orange graph here, we've seen that there are many, many antiderivatives, all that differ by a constant, right? All of these vertical shifts are all antiderivatives of that blue function. It may have occurred to you when we looked at this that, well, if we add one more piece of information, we could actually limit all of the antiderivatives down to just one possibility. If, in addition to knowing this blue function, if we also had some point and we wanted to find an antiderivative, one of the orange graphs, that goes through this point, there's only one antiderivative that will do it, right? We can shift the graph of the antiderivative vertically until we find the only antiderivative that goes through that point. It looks like that one would do the job. If we changed this point to some other point, maybe down here, we could again just shift the antiderivative vertically up and down until we find the antiderivative that goes through that particular point. So what this is telling us is that if we have a function and a point, we can find a particular antiderivative. There will be, hopefully, only one antiderivative that goes through that point. And that's the idea of an initial value problem. So if we have a function and a point, then we should be able to find an antiderivative that goes through that point. Right? This is an initial value problem. Notice that it's called an initial value problem because we have this initial value, this point that we want to go through, but it's still called an initial value problem even if the x-coordinate of this point isn't 0. Right? So it's slightly misleading because the initial value doesn't actually have to be at x equals 0, it could be anywhere. But the idea is always the same, right? If we have these two pieces of information and we want to find an antiderivative that goes through this point. So let's look at a couple examples. Let's find an antiderivative of cosine of x that goes through the point pi comma 1. Okay, well, the first thing that we can do is just find all antiderivatives of this function. So if we just calculate an antiderivative for cosine, well, that's sine. But remember, it's sine plus a constant, right? When we're just calculating the antiderivative, we don't know what this constant should be yet. So don't forget about it. Remember that this constant is there. So this is, let's call this capital F because this is our antiderivative. But we want our antiderivative to go through this point, pi comma 1. Well, that means that f of pi should be 1. Right? This equation is expressing the idea that our antiderivative, capital F, ought to go through this point. Well, we have a formula for capital F, right? It's up here. So what we can do now is turn around and plug this x value, pi, into our formula. And we get sine of pi plus c. So now we have an equation. 1 equals sine of pi plus c. And c is the only unknown thing left in this equation, so we can use this equation to find c. In fact, in this example, it's very easy to find c because sine of pi is 0, so this actually just says 1 equals c. So you can see this extra piece of information, this point, lets us determine which constant we want out of the many that are possible. So our antiderivative, the only antiderivative that goes through this point, is sine x plus 1. And this is an antiderivative of cosine, right? If you take the derivative of sine x plus 1, you do get cosine x, but it also goes through this point. And this is the only antiderivative of cosine x that goes through this point. Let's look at one more example. If the graph of a function, g of x, goes through this point, 2 comma minus 5, and the derivative of g of x is g prime, which is 3x squared minus 3x plus 1, let's find the function g of x. Well, since we know the derivative of g of x, right? So we know that g prime is 3x squared minus 3x plus 1. What we can do is do an antiderivative on both sides. Okay, well, the antiderivative of g prime is g of x. And now we can write down the antiderivative of 3x squared minus 3x plus 1. So that's x cubed minus 3 halves x squared plus x plus a constant. Okay. Now, you might be wondering, hey, don't I need a plus a constant on the other side? And the answer is, well, kind of, but not really. If you do write down a constant for this antiderivative, then you can subtract that constant from both sides. That gives us a minus d over here. But if c is an arbitrary constant and d is an arbitrary constant, c minus d is also an arbitrary constant. What should we name it? Why don't we just call it c? Right. So if you have more than one arbitrary constant coming from doing an antiderivative, you can collapse them down into one if they're being added or subtracted like this. Okay, so we have a partial formula for g of x. Right? We know that g of x is x cubed minus 3 halves x squared plus x plus some constant, but we don't know what this constant is yet. Now remember, we have this extra information. The graph of our function g of x should go through this point, but that means that g of 2 should be minus 5, right? Because if the graph goes through the point 2 comma minus 5, well, that means that it's going through the point 2 comma g of 2. That means g of 2 has to be minus 5. But now, just like in our last example, now that we know that minus 5 is g of 2, we can take this x value and plug it into our formula over here. So we get 2 cubed minus 3 halves 2 squared plus 2 plus c. And now we have an equation that we can use to solve for c. So we get minus 5 equals, let's see, 8 minus, 3 over 2 times 2 squared, that's 6, plus 2 plus c. So this is going to be, 10 minus 6 is 4, so minus 5 equals 4 plus c. And so c is minus 9. And now we know what g of x is. We've found the only antiderivative of g prime that goes through that point. So it's x cubed minus 3 halves x squared plus x minus 9, right? Because plus negative 9 is minus 9. So if you have any function that you want an antiderivative for and a single point, you can find an antiderivative that goes through that point just by calculating the antiderivative, plugging in the point that you know, and finding the unknown constant.